Hello, everyone. I hope you've been having a great day so far. I'm Ivan Herrera. As Ricardo mentioned, I'm a fellow Ignite team member from the Mexico team, and I'm currently working as a cloud developer here at Atos. Today, I want to talk to you about this topic that I think is crucial for our careers, which is about the ongoing learning challenges that we have to deal on a daily basis. I think this will be pretty relatable for the Ignitees, and not only for them, because on the Ignite, on the entire Atos and the IT industry, this is something you have to do constantly. So I hope you can get something out of this conversation. But the way I will approach this is by leveraging some of the machine learning and deep learning analogies, techniques, and methods used to train those intelligence and how we can use those methods into our own learning philosophies. So hopefully you can learn that and as well some basic machine learning concepts. And I want to approach this by talking about a phenomenon which I'm really amazed by that is called emergence. To introduce it, I will read this quote from John Rennie that states that you could spend a lifetime studying an individual water molecule and never deduce the precise hardness or slipperiness of ice. Watch alone and under a microscope for as long as you like, and you still couldn't predict that thousands of them might collaboratively build bridges with their bodies to span gaps. This talks about the emergence phenomenon. That is the idea that all of the complex systems that we have anywhere in the universe come from relatively simple building blocks. We have many examples: our planet's climate, the technology we develop, communication systems, social interactions, our universe itself, computer science, and IT. And I hope you see where I'm going with this and why this emergence phenomenon will be relevant to the discussion. And my first real experience with this whole emergence thing was when I was in college. I was doing my bachelor in electronics, and I was really amazed by the fact that the building blocks of electronics, which is quite a field that, is responsible for us having complex communication systems, internet, computers, cell phones, and pretty much the reason we're talking right now, has no more than 10 building pieces. Of course, each one has tons of variations, but the fact that so simple building pieces are capable of building something as complex as electronics today and be able to shape our entire culture, it was something that really amazed me, but at the same time, it is easy to feel overwhelmed by this idea because you have to learn all the possible complex connections you can do with all of these devices and components. I think the best way to approach this from a perspective shift situation is not to see it as a complex thing you have to learn, but rather as a beautiful thing that these small building pieces are capable of doing something so big. And why is this relevant at all for this talk? Because as I mentioned in the introduction, we are dealing with ongoing learning challenges all the time. This is what was going to happen when we got into this field. We know what was up ahead. And basically, education isn't something you can finish. Why? Because of the emergence phenomenon, the world is constantly changing and we need to keep up with that. How can we do that? By becoming autonomous learners that are able to learn new technologies every day. However, when we were at school or at college, to learn was something we could do, I don't want to say easily, but we had our entire attention to do that. We have teachers and colleagues that would help us. And today we have to keep up with work, learning, developing, and having a life, right? So what is the goal of all of this? To become better and better. And it sounds pretty, but at the end, this is a challenge for our brains because we're constantly trying to put knowledge into it. And well, there's nothing else we can do. We have to accept these facts if we want to become relevant professionals and be able to endure this challenge properly. And emergence is a thing, but is it a thing also in technology? That is precisely the case. Right now, I want you to think about where we stand technologically. We are literally now capable of building complex solutions from our home, build complex architectures with a few clicks, and using and leveraging all tons of current technologies that are relevant for our industry. On a deep perspective, I think we are orchestrating billions of electrons every day to build great solutions for our enterprise. And that is amazing, and it's great to think about that. However, the fact that emergence is into technology as well means that whenever we master a technology, a new one will arise. And we have to learn how to use that technology and properly use it into our skill set. What can we do to do this? Complexity is a thing that we cannot escape from. We need to accept it for where it is. And even if it can be challenging, I think it is what keeps IT and most fields interesting and relevant. And the advices that I will give to you is that what if I think that we can not only learn of machine learning, but also learn from machine learning? And I think we can. I think that I'm not going to take this whole learning advices from a psychological or neurological way because I am either of those professions, but I can share with you some of the way machines are learning today and how there is a great relation between that and the way we as humans learn as well. But are these just analogies, or is there some common things we share as humans and our machines? Deep learning is the field of artificial intelligence that leverages or inspires itself from the idea of the neurons that we have in our brains to build neural networks that can learn and solve problems. The neuron is the building piece that we have in our brains, and it is a perfect example of the emergence phenomenon because thanks to it, I mean, we're talking right now, we have consciousness and all of these sort of complicated things that we don't understand yet that well. I want you to know about the power of neurons on a deep learning perspective. I will show you this example right here. We have a problem in which we are supposed to label a set of points with a color, right? It can be either orange or it can be blue. And we're using only 6 neurons to come up with a solution for this. You can see that after this is run, it only takes a few seconds for the algorithm to tell that this is where blue points should be and this is where orange points should be. Only 6 neurons are capable of doing that. And we have billions of them in our brains, so we can take that relation and really feel the power our brains have. A more complicated problem, which is not classification of points, but regression. We don't want to give these points a color. We want to give them, we want to give them a color, but not in orange or blue, but rather in the whole spectrum between those two colors. It is a regression problem, and only 8 neurons can do the trick, as you can see here in the graph. Well, even if I do believe that the analogies that I will present you are great and are, solid, I do want to state that even though the actual working of the machine and the human are similar, they are different. And I am not saying that the exact same algorithms are happening inside our brains, but the overall same idea is because we share that same neural network structure, if you will. So let's begin first by, before I talk about the actual analogies, I want to tell you about what a neural network actually is so you can understand better these examples. A neural network is nothing but the complex connection of neurons, right? And what are neurons? It's not like we're putting little neurons in our computers and making them work. Neurons are nothing but mathematical functions that perform operations to their inputs. And in all of these interconnections that they have, they make a flow of information and they deliver a result, right? They have 3 main parameters, which are the weight, the bias, and the activation function. The weight is the value that it multiplies its input for. The bias, it is a value that it adds or subtracts to it. And the activation function is a specific mathematical function that it convolutes the input with. I'm not going to talk about activation functions, only about the weight and the bias, okay? And these neural networks, they don't come out of the box. You have to train them so they can properly solve a problem. And how do you train a neural network? Basically, you need to feed your data set into it. And with this backpropagation process that I will explain to you, it will learn. Let's see an example. Imagine we're going to, or we want to predict the cost of a house. And we know we have, I don't know, a table of some features of the house and the actual cost that house has. The features are the state, the average weather that place has, and the neighborhood, right? And based on that, we have a set of real values of costs of the house. At first, when we train and we pass the information through the network, it is going to give us a prediction. And that prediction will obviously be wrong, right? With that prediction, you can calculate the error of the prediction just by measuring the difference between the actual cost that house should have had and the thing you predicted, right? And then you take the difference and you feed forward that error back into the network. You literally back propagate the error. And as you do that, the parameters of the neurons are changed in such a particular way that it is learning from the error that it did on its prediction. Another common method for learning in the neural networks is what's called reinforcement learning. And it comes from the idea or the premise that intelligence have a set of actions and a set of possible outcomes to those actions. These outcomes can either be good, or they can either be bad. If you get a good outcome, you get a reward. If you get a bad outcome, you get a punishment, right? Take, for example, a Roomba vacuum cleaner. It's not like the manufacturer goes into your house and takes measures of everything and then programs the vacuum cleaner accordingly. That is not the case. It goes, of course, it has some pre-trained intelligence, so it doesn't bounce into anything, but it actually learns your house and the way everything is, the furniture and everything, by this whole reinforcement learning thing. When, for example, the actions this Roomba vacuum cleaner has is moving and picking up dirt, right? Also carrying a cat, as you can see. And a good action would be moving and not bouncing into anything. That would get a reward. Picking up dirt would also be a reward, because it indicates that that part of the house is usually dirty and that it should go there. A punishment should go when it moves and it bounces into anything, right? And don't worry about the vacuum cleaner. It's not actually being punished. It's not getting electrical shocks or anything. It's just an analogy, mathematical and algorithmic analogy that happens in the internal workings of the neural network it has. And what is the takeaway from this? What is the analogy we can use into our own learning? You have seen that on these examples, literally machines and neural networks learn from the errors that they do. That is the way they learn. And since they are neural networks at the end, and we share that nature, we learn by errors as well. It's not like something, that cliche, learn from your mistakes thing. It actually happens, and it is actually something that is used today in machine learning and deep learning. Another great example that I can come up with was network regularization. And to understand this, let's see the same example. You are using a great model, you train it perfectly, you use all the things you are supposed to do. You train it a little bit too much, and when it goes out and tries to learn from or predict real data, it doesn't perform nearly as good as it did with your training data, because it learned too much from the data set. The opposite can happen, and it is when your model is simply not complex enough to capture all the features your information has, so it simply doesn't predict good at all. The first one is called overfitting. You're overfitting your model into that data. The second one is underfitting. Your model is not complex enough to deal with a good prediction. And for me, this is the whole theory versus practice dilemma we have as humans. Whenever we're trying to learn something, we're maybe reading the documentation of a technology, we're practicing with isolated or controlled examples that perhaps a course might have, and then you go into real world problems and situations, use cases. There's always that trial and error thing that you have to come up with. So if you get stuck in theory and you never practice, you're going to be overfitted and you're not going to be properly able to deliver good results. How can you solve this? It turns out it's pretty much the same thing between overfitting and in us. We have something that is called, apparently I removed that slide, something called neural paths, that basically when we do something too often, it automates that process into our brains. And that is okay, because we have many things to do as humans. And if we didn't have those neural paths, we would have a hard time, pretty much doing anything daily. However, it is healthy to break these neural paths. And we do this by just going out of the routine and practicing with real examples, okay? Local minima. This is another issue that happens in machine learning. You want to ideally measure your model's performance so it's an accurate prediction what it does. And how do you do that? There are what are called loss functions. And loss functions are nothing but a plot between the average error you're getting when predicted with a particular set of parameters into your model. And of course, if you have many parameters, this would be a multi-dimensional graph that I'm not going to put here. So here's a 2D slice of it, if you will. And you can see how, ideally, you would want to have the set of parameters into your model that decreases the loss function the most you can. However, when you're going through this algorithm of decreasing the loss function, you can get stuck into something that is called local minima. We have here two examples of minima. One is local and one is global. This should be the greatest solution for your model, the optimal solution, and this is just a good one, but it's not the best solution you can come up with. If you get stuck at local minima, the neural network on its training is going to think that this is the best solution, and it's not really going to try to do anything else. It's going to stuck there, even if the performance is not that good. And as I told you before, we have those neural paths ourselves that kind of when we know how to do something. I will tell you a story for this. When I was in college again, electronics, we had to do circuit boards, right? To print our circuits and put the pieces in there and solder and everything. And everyone used a software, and I would use a different one because that was the first one I learned. And I knew the other one had like thousands of more advantages than the software that I used. But since I knew how to use that one, I didn't really want to shift that neural path into, I mean, at the time I didn't know what I was doing, right, in neural path perspective. But I stuck with that solution. And when I did try the other one, I realized that it was a way better solution that could have saved me lots of time on my career. And what is the solution for this local minima problem and this neural path thing we have, which is the analogous representation of that? It is literally to try things differently. For example, a stochastic gradient descent is the solution for this. And it basically means that every time you start at a random point of the loss function to find different minimas, and then you can compare which one is the best. So you can have an optimal model. The same goes for us. If you break the routine and you have to try new solutions, often you will find that they might be better solutions for the problems that you're facing currently. This is perhaps the most crucial part of the presentation, and not of the presentation, also of machine learning and deep learning training, the data quality. If you have data to train your model that is biased, that is inconsistent, incomplete, your model will be exactly like it. Your model will always be at most as good as the training data that you use to train it. That is just a fact. So you have to dedicate most of the time into your machine learning and deep learning training processing into finding good quality data and actually formatting it into the data expectations your model has. Because this is another thing. Models, even if you have great data, each one has particular learning needs and learning environments that you have to set and transform the data into a particular format that they like. And I think literally everything that I said about this data quality and model thing applies to us as humans, okay? Because if we dedicate more time into finding quality material and finding quality courses, documentation, we will have a way better time trying to learn a new solution than if we just take whatever course we find on YouTube. I'm not attacking YouTube. I love YouTube. Just an example. We have to do that so we can better learn new technologies and we can practice with them. And the other thing is about these learning environments that you have. We as humans have different learning needs. There are people that are visual learners, kinesthetic learners. You probably know about that already. And that is something that also happens in machine learning. Each model needs its data into a particular format, so it has to work properly. And it's something that if they don't take into consideration, the model simply won't do good at all. So we have to take that into consideration as well. Another thing is dimensionality reduction. This is a pretty brief example. Imagine we're again trying to predict the cost of a house. Again, weather, neighborhood, and state. But we're also now using as a feature the color of the front door. We can easily tell that it won't significantly or at all impact the cost of the house. So why should we use it in the first place, right? Our model, when training, is going to be paying attention to that feature that is not important. It's going to take longer to train. And it's probably going to deliver results that somehow relate to the color each house had that doesn't really capture the cost a house should have. So that is inefficient in a multiple category of ways. That is the same for us. If we're trying to do a solution with something, we're trying to learn a new technology, and we start considering things that are not useful. For example, I do believe it is important to learn a little bit of everything. But if you want to build a career in, I don't know, data science, and you then go and learn, I don't know, technology that you won't really use at all, like Ansible or something like that. I mean, it is good to learn it, but our attention is limited at the end of the day, and we have to properly distribute it to get better results. The final analogy for this presentation is ensemble learning. It is one of the most important ones, and you will see why in a minute. Imagine you're trying to predict whether if a credit card transaction is legitimate or fraudulent, right? This is a very important thing that happens today with our banks. And your requirements state that you need to meet at least 95% of precision when you're doing these predictions, right? And you're trying with multiple models and you simply cannot get it done. You get 80%, 90%, 87% accuracy, precision, I'm sorry, and you simply cannot get it done. So what do? You use all of your models together and let each one decide whether if that transaction is legitimate or fraudulent. It turns out that most of today's machine learning and deep learning challenges are solved with ensemble approaches. Instead of having this huge complex model, it is way better to have many models, more simple, if you will, that can better use their own strengths and weaknesses into doing a prediction. This is one of the most efficient methods we can use in machine learning. And as you can see, even machines can work as in teams through collaboration, and democracy works even for machines. So that is something. What I do like a lot about these analogies is that it's not like I'm just telling you, oh, you should do this. No, it actually works currently in the learning industry for machine learning, which I think is great. But at the end, we're more than neural networks. We do share the same fundamental pieces. We are similar, but at the end, we're different. Okay. So I do believe these analogies are pretty solid. However, we have to somehow shift them into our particular learning needs because we're humans with different goals, aspirations, backgrounds, and stories that we have to meet. And also we have more tools at our disposal. We have awareness, we have consciousness, more intelligence, and we have our colleagues and friends that can help us learn better technologies. So what are my advices to you as humans? I think you should always try to learn from someone else, specifically if you're in a big learning challenge, because it can save you lots of time. Because even if we're meant to learn from mistakes, as we saw in the previous examples, we can also learn from someone else's mistakes. So that's a real time saver. And in the process, you can really build your work and your teamwork. Another thing I want to mention is about understanding your attention span. I know you probably know about that 20 to 30 minute attention span we have. I won't really elaborate on that. Instead, I just want to tell you that it is okay to feel distracted once in a while. There is a time and a place for everything, but don't feel guilty if once in a while you feel the need to check your cell phone or you see a bird fly through the window. It is natural for us, and there's no need to feel guilty about that. Another thing is that we should recognize our progress. One great thing about this whole Ignite journey is that I can look back and see the progress me and my Ignite fellow members have progress so far. And it's very satisfying to see that progress. So I encourage you, even if you're still inside of the first sections of the Ignite program, to take a look back and see what you've learned so far. I promise you will find things that you have learned. And finally, as a conclusion for this, I want to encourage you to do and learn what you do, because at the end, each one of us has different goals and aspirations. And if our learning objectives don't match those aspirations, we're going to have a hard time learning something that probably doesn't mean that much for us in the first place. I know it's easier said than done, but I do encourage you to love what you do. And well, that is all from my side. I really hope you can take something out of this to your personal learning philosophies, or even learn some basic machine learning and deep learning concepts. And I encourage you to have a great rest of your day. Thank you for your attention.
Whoa. Amazing, Ivan. Thank you so much for that presentation. That was really, really great. Well, guys, it's already 11:59, and just on mark, it just turned 12. So with that, we're gonna draw the conclusion for today's talks. Thank you so much for coming, and we, as Ivan just mentioned, we all here. We hope you have a great day and an amazing weekend. See you next time. Bye bye.
Bye.
Thank you.